Hello everyone. So today we will be discussing the formation of stars, how the stars form, and how they produce this enormous amount of energy. For example, in case of our sun, we get that energy in the form of light, and we will make some simple estimates for how long certain processes can be sustained in the sun so that we can uh, get this energy from the sun. Okay, so this our discussion is all about how stars form. Okay, so we'll briefly discuss the concept of a black body and how this black body is related with the concept of color. And then before we go to the star formation, we actually will briefly discuss how the stars look like in the Hertzsprung Russell diagram, or we also call it HR diagram. HR diagram is a very fundamental graph between very fundamental quantities of the stars, and it can give you a lot of information about the stars. And then we move to the formation of stars and how the energy in the stars is released or produced in the first place. And then in the last we will make some simple estimates of sun, how much energy it can produce and how much energy we can get and how long this can furnish this much amount of energy. Okay, so the concept of a uh, black body is not a real physical object in the universe, but it's rather a theoretical concept that can be applied on the real world bodies so that we can make some simple calculations. So a black body is actually a perfect absorber that absorbs all the light that is incident on that body or falling on that body. That's why we call it the black. So if the light falls on a body and all the light is absorbed, then it means it's black, right? Because we usually see the things because of the reflection. And in the conditions of thermodynamic equilibrium, it also has to be not only a perfect absorber but also a perfect emitter. So it will emit the radiation also and it will absorb the radiation also. So so the most fundamental property of a black body is that the radiation a body emits. Okay, let's just assume that any body is a black body, because everything in this universe which is at the temperature higher than absolute zero, it emits some radiation. Even the humans and animals and all the living and the non-living objects around us, so all of them, they emit radiation. Now whether we can see that radiation or not, of course it depends on the temperature of the body. So the black body should have a spectrum that only depends on the temperature. So this function, it's called the Planck's law. It defines the spectrum or the spectral brightness of a body. So for example, here in this graph, you can see that if the temperature of a body is about 300 Kelvin, 300 Kelvin is roughly 25 degrees centigrade. That's the temperature of most of the objects around us, even the human body. So if the temperature of an object is 300 Kelvin or about 25 degrees centigrade, the spectrum of that body should look like this one. So this one. So you see that it has a peak and then the spectrum falls down. And then if you keep the increasing, then this peak, if you keep increasing the temperature, then the peaks moves to the higher frequency. So on the right side, you have the frequency, and on this y-axis, you have the intensity or the brightness. So, and then if you go like further at 4000 Kelvin, the temperature becomes like this, and at 7000 it becomes like this. So you see that the temperature nearly from 5000 Kelvin to 7000 Kelvins are the temperatures if the body has anybody has a temperature like this, this much high in a temperature, then its light will have a peak in the optical band, in the optical light that we can see. So on this side you have infrared and the microwave. On this side you have higher energy ultraviolet or X-rays, and these 7 colors you see here, these are the optical light, these ones. So luckily most stars, they have the temperature between 4000 to 7000 Kelvin, so we can see them in the optical band that our human eyes are evolved in the way that we can only see the optical light. So for example, the human body is 300 Kelvin, let's say almost, and it emits the infrared radiation. This first peak you see that's highlighted, it's 300 Kelvin. So this is infrared region. This is infrared region. So we cannot really see the infrared light. Luckily so, because if we could see the infrared light, there would be no concept of night, because all the bodies around us, even the human body, they emit in infrared radiation. And the temperature of our sun is nearly 6000 Kelvin. So it's exactly the peak should be in the visible spectrum, so we can see our sun. So this is the concept of a black body. And keep in mind that the peak frequency of this black body spectrum, it actually defines the color of object. So now this makes sense that why sun looks yellow, because yellow is actually the peak. If the sun has a temperature about 5800 Kelvin, then the peak is almost falls in the yellow band. Okay, so okay, so the color, so how the color and the concept of a black body, they are not related. So if we keep heating something, it usually can change the color. So for example, if you keep heating a steel rod, it will keep changing color. At first it will become red, then it will become slightly orange. If it's very hot, it becomes yellow, and if you can somehow make it more hot, it might turn into green or blue. So why does this change of color happens? Is because when we are heating a body, its temperature is increasing, and the peak of the black body spectrum moves from red to the blue side. Keep in mind that in the optical light we have the 7 colors. So here in this figure you have see these 7 colors. So on the right side you have the red. Okay, if we start from the left, first is the violet, then it's indigo, then it's blue, then it's green, then it's yellow, then it's orange, and then it's red. So there is a word called Vibgire, if you want to remember this. Keep in mind that the violet is the highest color. It's the high energy. It's the high energy, high frequency of light, and this red is usually the lowest energy, or the lower or the coolest color in the optical wave band. So now so does it mean that the green apple is hotter than a red apple? Apparently they are sitting on the same table. Keep in mind that the color of an object is not always an indication of the real temperature of a body. Why? Because nobody in this world is a perfect black body. So the simple explanation is that why some apples looks green and some looks red is because it depends on how much chlorophyll the apple has on its skin, because the chlorophyll absorbs other wavelengths and only or reflects the green. So so apparently both apple are same. It's just because of the reflection of or different lights that we see the different colors of an apple. But usually for a hot object, if it's a perfect in a black body, if it's near to a black body, there is no reflection. So in that sense, the color of a hot body is exactly the measure of its temperature. So we can make some simple equations. So we know that okay, let's call it the color temperature. So we know that the frequency of a light is f, and corresponding to each energy each frequency f, there is energy E. So this is for the light photons, and because the body is made of atoms, so we can consider it kind of a gas. So for a gas, you know, the energy of a gas is E is equal to kT. T is the temperature of the gas. So then if you make them equal, because this is E and this is E, so from here you can define that the temperature and the color, they are correlated like this. So the frequency and the temperature, they are correlated. Of course, this is only if you assume that there is an equilibrium between the light and the gas. Yeah. So human eyes can only detect the visible light. So the wavelength is from 400 to 800 nanometers, and in this range, all these colors actually we see, from starting from the violet ending in the red. So the violet is the highest energy color, or it's high temperature, and the red is the low temperature. So usually keep in mind that in astronomy, when we talk about the color of a star, so if the star looks blue, it means that it's hot, or if it looks violet or blue, it means if it's on the blue side, it's a hot star, and if the star looks red or orange or yellow, it means that the star is it's not very hot. And also keep in mind that the temperature is a local phenomena. So is the color. So what you see, if for example, if the sun looks yellow, that means that's yellow is the color of the surface of the sun, because the temperature inside the core of sun could be much higher, and that's usually the case. So, Hertzsprung-Russell diagram. So suppose that in the Milky Way you have 2 billion stars, 200 billion stars, and you measure the temperature and the brightness of each star, and then you plot this figure. So on this x-axis you plot the temperature, and on the y-axis you plot the brightness or the luminosity. Then this kind of a diagram is called HR diagram. So it's a graph between the luminosity and the temperature of stars. Now you see some interesting things in this graph, and keep in mind that this temperature axis is actually inverted. So it increases from the right to the left. So on the right side, the temperature is lower, and as it moves to the left, so the temperature gets higher. Somehow this is a convention how this graph is always made. So you see that so you see some groups of stars, right? So the largest group is this one, of course. You see that there is along this line, most of the stars, okay, you will find that 2 billion stars in the Milky Way, you will find that most of these stars will fall along this line. It's almost a straight line. And these are called main sequence stars, or we also call them dwarfs. So the dwarfs are main sequence stars, and they produce energy mainly by hydrogen fusion in the center of the star. Okay, and then you see there is a group which is not very bright, but it's very hot. So they are hot, so they are green and blue, so they are hot. But on the y-axis, it's not very high, it's low. So these are called the white dwarfs. So white dwarfs are usually made when these main sequence stars, which are called dwarfs, when they end up their life, they can become white dwarfs. So this is actually kind of the remnants of low mass stars, and in these stars no fusion is happening. So because no fusion is happening, not so much energy is produced, so they are very dim, they are not very bright. And then there is another group called red giants, or simply giants, along this line. So giants are actually, they are highly massive, and well, not very massive, but they are large in the size. So the star is very big, it's much bigger than the sun, and usually the color is red, so it means they are a bit cool, they are not very hot. And but along the y-axis you see they are quite high, so they are very bright, so they are cool but bright stars. And then there is a special branch called supergiants. They are high in mass, very high in luminosity also, but then the temperature is not very high. But because the size and the mass is very high, so they are extremely bright. So, so these are the basic 4 types of groups of stars that you will probably see not only in the Milky Way, anywhere in any galaxy. So if you have, let's say, trillions of stars, and you know their temperature and brightness, so you will. But have you noticed that most of the stars actually fall on the main sequence? So why it's like this? It's very interesting. So why is most of the stars are make in this group? Because this group actually lives for very long time. We will discuss this later a bit, that the hydrogen fusion is actually a very slow process, and because it's a very slow process, So at any given time, you will see that the most of the stars will be in this in a group. But then there is a question, for example, that okay, stars are usually not formed individually, but they are formed in the cluster at the same time when they form. So if all stars form at the same time, why there are different groups here? Let's say four groups here. So why there are four groups? So all of them should be in the same phase of their life, and all of them should be on the main sequence. So it all depends on the initial mass of the star when it was formed. So if all stars had same mass when they were formed, yes, all of them will be on the main sequence at a given time. But that's not the case. So you see other groups like giants and supergiants and white dwarfs. It's because different stars had the different mass when they were formed. Okay, some uses of HR diagram. They are very useful to for the stellar classification. For example, if you want to classify billions and trillions of stars, you will use this a diagram to classify them. They also help you. This diagram helps you to understand the evolution of stars, and also helps you to understand lots of properties and the distance and age of stars and so many things. Okay, one big question: where is our sun in this figure? So our sun is a yellow dwarf star. So it's a main sequence star. So and it's yellow. So it should be somewhere here along in this yellow group of stars on the main sequence. And these are some bright stars that we usually see on the night sky and how they look like in the HR diagram. So, for example, this is our sun, and these are some giant stars that we see in the night, like Arcturus and Antares, or Betelgeuse, or Rigel, or the pole star Polaris. Yeah, and there are many more bright stars that we can see in the night. So we see that all of them, they are not in the same class. So our sun is a dwarf star, but Antares and Betelgeuse are red giants or supergiants, and Aurigal is a kind of a blue giant star. So they are different type of stars. So yeah, now we come to our main question: how stars form. So what is a star? A star is a glowing sphere of self-gravitating hydrogen gas, a sphere. So it's kind of a gas cloud that is sustaining itself due to the gravity, and it's also the glowing. So it means that it's producing energy or light in the center. So this is a kind of a textbook or a simple definition of a star. So our question is how stars form. So what happens initially, that there is a gas in a cloud. It's not in a burning yet. It's not producing any energy or light. But somehow, if this gas in a cloud can collapse, and there are many reasons why these gas clouds can collapse. So one reason is that if the mass of the cloud keep increasing, because the bodies attract each other. So there is a big gas cloud, it will attract other gas also, and it will become big enough to collapse on itself. There is a limit, there is a mass limit called Jeans mass limit. So if the gas cloud is higher than the Jeans mass limit, it will just collapse on itself. So there is this molecular hydrogen gas, and it will start to collapse on itself. So this collapse leads. So you know that when the gas is compressed, it becomes hot. So when this collapse happens, then the star starts to become hot and dense, and we call it initial star, or the protostar, or a baby star, like whatever you want to say. At this time, it's just hot. It's not producing some light. It's just the gas is becoming hot and hot as it's collapsing. And somehow, okay, whenever there is a gravitational collapse of a gas, so it's not linear. So the gas has to spiral into a center of mass, or the gravity. So this makes kind of a disk around the protostar. So how this protostars form? Actually, in the start there is the collapse happening, and then the disk is formed, and then this protostar can keep eating more and more gas from the disk. So now we have a condition in which there is a collapsing object, a collapsing in a cloud of gas. It's becoming hot and hot, and when the temperature reaches roughly 10 million Kelvin, the hydrogen gas ignites itself due to the nuclear fusion. Keep in mind that the hydrogen gas, when it becoming hot protostar, it's already ionized, and then it loses electrons, and what a hydrogen atom is just a proton and the electron. So if the electron is removed, what you are left is just the protons. So it's a protonic gas. So the proton and proton, you know that they are both positive charges, and the positive charges repel each other. So you need very high temperature to fuse them together. So at the temperature of roughly 10 million Kelvin, the hydrogen gas nuclei, they start to just fuse into helium. So hydrogen can start burning into helium, and this process is called nuclear fusion. By the way, it's not always the case that you need the 10 million Kelvin temperature, because of the quantum or tunneling effect. So the nuclear fusion can start even at the lower temperature. If there was no quantum mechanics, probably a star would never start, because the 10 million Kelvin is a very high temperature, and it's probably cannot be achieved so easily. So now there is a condition. So the sun, so the protostar is collapsing. So the star is collapsing. So it's attracting itself, and then because of the fusion, some energy is produced. This is usually the kinetic energy, and it's happening in the center. So it will make the star expand. So there is a competition between two things: attraction and expansion. So what it will happen, that it will at some point it will reach equilibrium. So this equilibrium is called hydrostatic equilibrium. This remains for very long time, and there is an equation. So in this equation, on the left side you have this outward pressure, and on the right side you have this inward pressure by the gravity, and they are equal, so they are balanced. So when the stars starts to fuse hydrogen, they starts like burning hydrogen gas into helium and produce energy and light. This phase is hydrostatic equilibrium, and this is a very long time phase. Why? Because hydrogen fusion is a very slow process, and at this time, this star is actually a main sequence star. like our sun. So our sun is in this era. So this is actually our it's a very long phase, and our sun can live for a very long time because it's a main sequence star. So so how it will so what's the main important parameter that will define how quickly stars will evolve into how it will lead to the death. So the death of star will be, let's say, immediate, or it will be very very long time. So it all depends on the initial mass of the cloud. So if the mass of the cloud is, let's say, one solar mass like our sun, then these stars live for very long because they spend most of their time on the main sequence. But if the mass is very low enough that it will not ignite, it cannot collapse, that it can reach the 10 million or temperature, or it cannot start fusion, then these stars will end up, we call them the brown dwarf. So the brown dwarf is actually a failed star. It cannot, it does not has enough mass that it can ignite the hydrogen burning. Okay, so yeah, this is a schematic diagram starting from, okay, so in the start you have a gas cloud, and then this cloud starts to collapse on itself, and this is you make a protostar and the disk around the protostar, and then you have this envelope, this gas envelope around the star, and then because of this disk, keep in mind that the planets, they are formed in the disk. So what's happening is that there is this in the disk, it's the disk is relatively cold, so it's more easy to make the molecules in the disk, and those molecules can condense themselves and make the planets. And then when the planets form, we have a whole planetary system in which you have a sun in the center, and then you have these dots, these the planets. So almost all stars have make the planets. So this disk is sometime or called the planetary disk. So this central star, it keep eating more and more gas from the disk, and they keep the hydrogen burning, keep going, and this process remains active for a very long time. So yeah, the type of stars, this is how they look like. So on the top you have these giant stars, and in the low panel you have this dwarf star, or the main sequence, or the sun-like stars. So in the giants you have the red giant, or the red supergiant, or even a blue giant. And in the dwarf stars we have the white dwarf, which is the last end of a star for a sun-like star. So let's say the white dwarfs are the remnants of sun-like stars. And then we have the yellow dwarf star. So our sun is basically this one. So our sun is a yellow dwarf. And then you also have the red dwarf and the brown dwarfs. So the brown dwarfs are the failed stars. So if they don't have enough mass, so they cannot burn hydrogen, so they will just die out. Okay, so yeah, now the main question: how energy is produced? So the question is, why do we believe that the energy in the sun is produced by the fusion? Why not other processes? So we know that energy can be converted from one form to other form, right? This is easy, but so the sun is self gravitating in a cloud of hydrogen gas, so it has some gravitational energy. So one scenario is that, for example, if there is this huge amount of gravitational energy, and if this energy can be converted into light, so how long time this can survive? So one scenario is this one, and the other scenario is that the fusion, that the so okay, so let's first discuss the gravitational scenario. So here are some parameters of the sun. As we know that the sun has a mass about 10 to power 30 kilogram. It's very, very massive. It has a radius almost of 695,000 kilometers, and it's very dense. The density is nearly 1400 kilogram per meter cube, and the luminosity of sun is also very high. It's 10 to power 26 watts. So so you know that 100-watt bulb, right? How much energy, how much light it produced. So the sun is 10 to power 26 watts. It's not 100, it's 10 to power 26. Okay, so first scenario is that, okay, you have this is a sun as a gravitational in a cloud of hydrogen gas, and the gravitational energy available to be converted into light is this much. So the formula is G for the gravitational. So this gravitational energy Eg is equal to Gm square over R. And the answer, if we put these numbers, so the answer is about 4 multiplied by 10 to power 41 joule. This is huge amount of energy. But the question is how long this energy can be released. So what is the lifetime or the time scale of the process in which this gravitational energy can be totally converted into light? So if we are assuming that this gas cloud, which has the gravitational energy, it will just collapse on itself, and there is no such thing to stop the collapse. We call it the free fall. So if it's a totally a free fall case, it's only the if we calculate the time scale or the age of this whole process, it's only 30 minutes. Why? Because the collapse keeps accelerating. There is no such thing to stop this collapse. So it's very low time. So it means that if the sun has to collapse and there is no such thing which is opposing the sun to collapse, then it will just collapse in half an hour. So it means that this in a process cannot be the main process of energy release, because if this was the process, that the sun would have been gone in half an hour. Now suppose that that the sun releases the gravitational energy on the Kelvin-Helmholtz time scale. So it means that the sun will keep emitting the energy, but at this rate. So L is it. So the luminosity of sun will be constant. So 3.8 multiplied by 10 to the raised power 26 watts. So if at this constant power the sun keeps converting the gravitational energy, and then the total time that it can survive is 30 million years, which is quite higher than 30 minutes. Now why this is higher? Because it's not accelerating case, so the sun will keep emitting the same amount of energy. So if this is the case, then the sun should be gone by 30 million years. Sun cannot survive more than 30 million years. But we know that the earth is 45 billion years old. So let's say that Earth was formed nearly very soon after the Sun. So it means that the Sun is at least 405 billion years old. So if this is the case, it means that this gravitational energy scenario is wrong, because this can only sustain the Sun for 30 million years. So now the alternate scenario is fusion, that the energy produced or the light coming from the sun, it's produced by the fusion, not by converting the gravitational energy. So the fusion, most of you know the Einstein's famous equation E is equal to mc square, so that the mass and energy, they are equivalent and they can be converted into one another. So assuming that the sun, you have a 10% mass actively involved in the fusion, and the efficiency is 7%. So it means that the 0.7%. So it means that the 0.7% of that energy can be converted into the energy that we see. That for a given luminosity, okay, this is a bit higher, this is 10 to power 44, so this is a very high energy. It's higher than the gravitational energy, which was 10 to power 41, so it's 10 to power 44. It's 1000 times higher at least. So this fusion energy, so fusion is a very effective way to convert mass into energy, and even if the efficiency is low, just 0.7%, but we will see, and even if only the 10% mass of the sun is actively involved in the process, so it can still sustain the sun for the 10 billion years. So this TF is actually the fusion time scale. So the time scale is 10 billion years. So it means that if the energy of sun is being produced by the fusion, so the sun can survive for 10 billion years. So we have already spent 4.5 billion years, so it means that about 5.5 billion years we still have. So it's still long, so we are halfway basically. So yeah, so how this fusion happens, this energy is produced. So this famous equation E is equal to mc squared. So keep in mind that this is a c squared. So c is a very high number. So even if m is small, but when it's multiplied by the square of c, it becomes very high. So a very small mass, when it's converted into energy through fusion, we can get a lot of energy. So this is the main thing. So the stars burn their gas fuel through the nuclear fusion, mainly the hydrogen fusion. So in that sense, actually, the sun is or any star is basically a controlled fusion in a reactor or a thermonuclear reactor that people have tried for over the decades to make on Earth, but it's not easy to constrain the plasma, but the nature does it so perfectly. Yeah. Okay, so what happens in the fusion is that the hydrogen and hydrogen, it actually fuse into helium. So the problem is that the mass of the helium should be same as the total mass of the hydrogen that fused, but that's not the case. So usually there is a difference between the reactants and the products. So the reactants are hydrogen atoms and hydrogen nuclei, and the products is the helium nuclei. So there is a slight difference of mass. That difference of mass is actually released as energy. So this is the fusion in a process. Now there are two methods by which the hydrogen at nuclei can fuse into the helium nuclei. So one is called the pp chain or the proton-proton chain. So keep in mind that the hydrogen nuclei is actually a proton. So what happens is that in this process 4 protons, so this 4 hydrogen nuclei, they fuse into one helium nuclei, and each reaction gives you about 26.7 mega electron volt energy. This energy is quite high. So it means that the 4 nuclei of hydrogen will give you 1 nuclei of helium, but in this process you get 26.7 mega electron volt energy. Now because this pp chain is a slow process, so it can make the star stable for billions of years, as we already discussed before, that the fusion can sustain the sun for 10 billion years. But this same reaction can happen in another way. It's called CNO cycle. So in this CNO cycle, the carbon, nitrogen and oxygen nuclei, they act as a catalyst. So they help the hydrogen to fuse into helium, but they are not used by themselves. So the reaction is still the same and the energy we get is still the same, but this process is very fast. Keep in mind, and it only happens in the massive stars, the stars that are highly massive, more than the mass of sun. So we have two competitors here for the fusion. One is the pp chain mechanism and one is the CNO cycle mechanism. I will show you in a bit of detail. So yeah, here so this is the pp chain. So what happens is that you have these two chains. So this chain is 2 protons fuse into each other, 2 protons fuse into each other, and the end result is that you have this helium nuclei. Okay, and then we have this CNO cycle, which is fast process, and in which what happens is that you have a carbon 12 nuclei, and it eat up one hydrogen nuclei, and it become nitrogen 13, and then this can decay into carbon 13, and then the carbon 13 will eat one more hydrogen to make nitrogen 14, and the nitrogen 14 will eat one more hydrogen atom to make oxygen 15, and oxygen 15 will again it will first decay into the nitrogen 15, and the nitrogen 15 can, when it eats one more hydrogen, it can become helium. It can become helium, or maybe 4 heliums, because you have to conserve the mass number 16. Okay, so this process is fast. So this CNO cycle is actually very fast process. So, and keep in mind that the CNO, they are made in the first place in the massive star only. So what happens is that if the initial mass of the sun is very high, so when this carbon, nitrogen and oxygen, when they are formed, they will help the hydrogen fuse much faster. So what happens is that the massive stars, they die earlier than the low mass stars like our sun. So both processes are equivalent. They both release in one reaction, they release 26.7 MeV energy. So let's make some simple estimates. for our sun. So we know that the mass of 4 hydrogen is this much units, and we also know that the mass of helium is 4.002603 units. So there is a mass difference between the reactant and the product, and this mass difference is 0.0287 units, and this, if you multiply by c square, this will give you 26.7 MeV energy. Okay, this is for one reaction only. So we want to see that how many reactions should be happening in 1 second if we want to get the energy from the sun as much as we get. So so we know that the luminosity of the sun is 10 to power 26 watts. So it means that so it means that the 26 joules per second. So 26 joules of energy, 10 to power 26 joules of energy is produced in the sun in 1 second. So now we know by definition that the luminosity is energy over time. Okay, and so one reaction produce energy E. So we need to multiply by N and divided by T. So this will be the definition of luminosity. So let's say that we isolate N over T, and this is called the reaction rate, and then it becomes equal to L over E. So now we know the value of L, we know the value of E. E is a 26.7 mega electron volt, and L is 10 to power 26 watts. And if we if we divide them, then the rate of reaction we get is 10 to power 37 reactions per second. So it means that sun has to fuse hydrogen very fast. So it means that 10 to power 37 fusion reactions should happen in 1 second in the sun to produce 10 to the power 26 watts of energy. So, and okay, as we are losing, so the fusion is happening, and more hydrogen is produced into helium. So we are losing the fuel, we are losing the mass. So how much mass we are losing? So the mass loss rate we can calculate. So we know that the energy is mass multiplied by c square. Okay, if we divide by time on both sides, so this energy over time, this becomes luminosity. So we also divide by time on this side. So this we can isolate from this equation mass over time. This is called the mass loss rate, and then it becomes L over c square. So the L we know is 10 to power 26 watts, and c square is a constant, and if we get the answer is 4.10 to power 9 kilogram per second. This is the mass loss rate. So that means that sun burns nearly 4 billion kilogram of hydrogen every second to produce the energy that we see here on Earth. Okay, not all the energy we see here on Earth. We only see a part of that energy that is irradiated in the form of light. So this is basically the case. So these simple estimates can tell you that sun can be sustained for a very long time. So sun is nearly the half of the age as it is promised by science. So it means that the sun is roughly 5 billion years old, and it still have the 5 billion years to go. Okay, and in the last we'll tell you how the stars are classified. So we know that the stars show a different color because of the different temperature, and they have a different brightness. And also if you see their line spectrum, because some of that some of that light is absorbed by what kind of atoms or nuclei you have in the sun. So all of these three parameters can give you a classification of stars. So this is a Morgan Keenan system. So you can classify the stars based on, usually it is based on two categories. So one is the temperature class, and then is the luminosity class. So in the temperature class, O means the hottest and M means the coolest. Of course, there are other between them, like O and B and A and all the way to M. And all of these stars, they have the different temperature range, and they have the different size and so on. So and they have even like further classes into each letter, like O goes from 0 to 9, B goes to 0 to 9, and all the way even M goes from 0 to 9. So this is the temperature classification. So one way to classify is how bright is the star. So the luminosity class. So in the luminosity class, it runs from 0 to 8. So 0 means the brightest star, and the 8 means the very dim stars like white dwarf. So now if you combine two of them, so for example, sun is a G25 type star. So it means that it's a G star, and with the temperature class 2, and it has a luminosity class 5. So it's a G25 star. So this is how the stars are classified. So yeah, in today's discussion, we saw how stars are formed and how they produce the energy, and how long they can sustain with this scenario. So the one other important question is how stars evolve in time and how they end. This is a very big topic on its own, and depending on what kind of star it is in the start, it will not define how it will end. So maybe we will discuss this in another video. And so for now, I would sign off. So see you another time. Okay, bye bye.